You're right here.
My apologies for this being tardy with coming here in the presentation. I'm Thomas Schultes. I am a professor of computational physics at ETH Zurich, and I lead and direct the Swiss National Supercomputing Center for 16 years, where we are designing and building a research infrastructure and serving the Swiss ecosystem. And as such, we've been involved with some of the Swiss engagements of the Square Kilometer Array project. And I guess over the past few years, I've made some observations and given some thoughts on how one might move forward with this question of SKA and MWA, the last question of the previous talk. And I was also a few times in Perth, actually already twice this year in Australia, and we had discussions, and somehow it was suggested that I give you some overview of what we are doing in Switzerland in terms of research infrastructure and digital infrastructures. And then I will conclude the presentation. I hope I will stay well within my time, so to come with some suggestions or thoughts on how radio astronomy may work in the future. Like my background is condensed matter physics. I've been involved in my previous life before being here in Switzerland with building. I was working for Office of Science Labs of DOE, Department of Energy in the US, and involved in developing large research infrastructures, both on the computing and on the experimental side. And but I'm not a radio astronomer, so I know a little bit of what the workflows and so on. I try to so I'm not going to pretend I am in my presentation. I will just honestly tell you what we are doing. I will use some examples, and I hope you can see the analogy between the different infrastructures and where I might be going then in the end with the suggestion. I was, I guess, born for Apple, Macintosh, and very unused to using Windows systems. So this will probably be my struggle here today. Okay, so let me tell you about ALPS and the context. We are an institution of the ETH domain. To be more specific, we are a research facility that is located in the south of Switzerland, in Lugano. We are part of, is this, what am I doing wrong? We are part of ETH Zurich, organizationally, but we serve the entire Swiss research community. And as such, we are also an open access research infrastructure for the whole world. In the ETH domain, we have, besides ETH Zurich, we have EPFL, which is where we are today. The schools are probably comparable in many ways. And then we have a number of national labs. One of the most important one is the Paul Scherrer Institute. Well, they are all important, but the largest one is Paul Scherrer Institute. That, given my past experience, I can say you can compare to one of the Office of Science Labs or the Jülich Forschungszentrum Jülich in Germany, just to give you some references. Okay, like I said, I'm a bit struggling with this. Is there a way to, okay, yeah. And so there are a number of further labs. I will leave it at that. One is a materials lab, some environmental labs. And our mission at CSES is to develop and operate high performance computing, and since 2015, a data research infrastructure that supports world-class science in Switzerland. You can ask, why are we in Lugano? Why are we not closer to some of the, like we could be in Villingen at the Paul Scherrer Institute? Well, there are always, for these things, there are political reasons, but there are actually practical reasons. The distance is not really very important. It's only a few hundred kilometers. And we have this incredibly powerful academic network in Switzerland. Today, we can sustain between any of these relevant research infrastructure 400 gigabits per second without too much cost. And we could push it higher, but then it starts to cost. And so a few hundred kilometers is just, milliseconds away, and which is a latency you can tolerate. We have in Switzerland the Large Hadron Collider in Geneva that you all know about. We have the Paul Scherrer Institute. I will go a bit in more detail. And then another very important stakeholder of ours is the Swiss Meteorological Service, or Meteoswiss, that I will explain. The Paul Scherrer Institute has, if I count right, 4 very large experimental user facilities. One is the Swiss free electron laser, the Swiss light source, which is the latest generation synchrotron light source, then a neutron source, SynQ, that's a spallation source, and a muon source. If you can accelerate protons, you can create neutrons and muons. And so they really make the maximum out of what they have. And so these are 4 what we call user laboratories. One second. Okay. So good. 4 user laboratories. So these are open access research infrastructures. And we are the 5th in Switzerland for supercomputing, and we operate a user program. And so any computational scientist, in fact, whether Swiss or non-Swiss, can apply for resources with and then go, submit to a peer-reviewed, transparent process. And we operate, besides the user program, also a platform. We call it Platform for Advanced Scientific Computing, which is the intent of this platform is to develop future software, mathematical algorithmic capabilities. And it turns out that one of the teams from the Swiss, from here actually, EPFL, that is participating in the XK project has one of these past projects, and that is there to develop algorithms. Our current flagship infrastructure is this machine called BitStein, which is in operation since 2013 and has been upgraded in 2017. This was a midlife upgrade. And you can imagine, you have to imagine it consists of about 5,000 GPU accelerated nodes and about 1,500 or 1,400 multi-core nodes. And so we've been operating GPUs in production since slightly over 10 years now. Now we are talking now about the successor infrastructure and some just background on the naming. So these are the Alps, and BitStein is one of the mountains in the Alps. And so we have a tradition to call supercomputers and clusters after peaks, mountains in the Alps. And the main subject of what I'm trying to get across here is that the infrastructure we build should no longer be seen as a monolithic supercomputer or HPC system. It is a supercomputer. It performs just like any other like some of the top 10 supercomputers. In fact, it's also listed in the top 10 of the top 500 list, but it is going to be separable into many different supercomputers. So we will have many peaks, and then we call the infrastructure after the mountain range. That's the logic behind this. I mentioned one of our very important stakeholders is MWA, and so please view the meteorological community as kind of an equivalent of SKA. Obviously, here we talk about very large simulations and very large data. Maybe in SKA or MWA, we have less simulations and more data analytics, but the social structure behind it could be comparable, or I guess there is a lot to learn there. Now, MWA has been in the business of modeling since the early 90s. Since slightly over 20 years, they've been running their infrastructure at CSES, at our center. Since 2008, they were pushed into high-resolution simulations, and since 2016, we are actually simulating a model at kilometer scale, which is what you have to do if you want to have a chance of having a good numerical weather forecasting in the orography of the Alps, where you just need the grid to be able to resolve some of the main valleys that we have. And but the way to think about MWA is not just about simulations, but also about a huge network of sensors, measurement stations, satellites that take in a lot of data that is organized and then assimilated into the model, and that then produces the forecast. So there is a huge aspect of data that is already coming in here. And in fact, MWA is a member of the European Center for Mid-Range Weather Forecasting, one of the founding members, a very fine organization in Europe that exists since the 70s and is one of the leading organizations worldwide. In fact, I remember in the US, the integrated forecasting system, IFS, that ECMWF operates is called the European model, which is the most reliable model also for predicting paths of hurricanes in the US. So a very strong organization, and the relevance, I would say, for this discussion is you have now countries, every one of the member states has strategically their own weather forecasting infrastructure organization, and then they cooperate at the continental level. And you see there are countries, even Israel and North Africa, Turkey, and so are members of this organization. And it works extremely well. I will come back later why this is so relevant for our infrastructure design. But with these partners that we have, our vision is, or ambition is, to be the leading partner for extreme computing and data solutions that best serve the evolving needs of science. And if there's something that is changing, is fundamentally changing, is the way science is relying on data and numerical algorithms to make sense of data. And I guess your experiences in the MWA and your others experience the same situation. And so Switzerland is dealing with a challenge. We have these new instruments at the Paul Scherrer Institute. We have a lot of new instruments at MWA that generate huge amounts of data that need to somehow be analyzed. And the problem is we don't even understand the real scale at which we have to operate. But what we know is once the instruments are done, produce data, we have to be ready with the infrastructure. But we cannot specify in advance really what we have to do. And I guess this probably sounds familiar with the things you are experiencing. So we were confronted with this problem, and there were, particularly from the computer science side, there was a big tendency to declare big data analytics as like a fourth pillar of science. And there is an interpretation in science that we have experiments and theory and we have simulation as a third pillar, and then big data analytics or data science as a fourth. I myself, I'm skeptical of these interpretations. I had at some point one of my colleagues actually convinced me that simulation and theory is kind of different, but today, after maybe 20 years later, I kind of go back and say simulation is a way of solving mathematical problems, and then data analytics is another way of doing statistics, and the methods that we have today are immensely powerful, and the tools, the machines we have, the software we have are powerful. So, you know, this may be one way to see the thing, but it doesn't have to be this way. What is more practical is to just, you can ask ChatGPT about big data or big data analytics, and you will receive the answer that when you deal with this, you are dealing with 4 aspects of data, namely the velocity, the volume, the veracity, variety, and the value of data. And this now explains also why the meteorological community, and particularly ECMWF, is such a good partner. Okay. So okay, now I guess I figured it out. Namely, it turns out that ECMWF has, since the 80s, you can really go back in the history, so 40 years of experience with all these aspects of big data. They've even developed what we now call object store, a key value store system that they put in operation in the mid-80s. And they push the limits on each of these 5 aspects of big data. So for us, when we were developing ALPS, it was quite clear. When you develop even a computing infrastructure, you should not design it for the top 500 list. That's the mistake many made. You should design it for something. And it's a general purpose. It's a general purpose, and you don't really know where to go, like I said before. Then you just take the biggest problem that is out there, the biggest known problem, and you design for that. And that's what we did. And here ETH Zurich was very, very also visionary, or we had colleagues in the meteorological and climate community that worked with us in creating this project called Exclaim, which is a very targeted investment in developing simulation infrastructure, software infrastructure. And this is in collaboration with the climate scientists and with MeteoSwiss. So the software we use here is the same software we use for the service for MeteoSwiss. And with this, we are guaranteed to cover also then all the data aspects as we are developing things along. But now let me explain ALPS from a computing point of view. What you have to imagine, ALPS is a very high performance network. I will not go into the detail. It's called the Cray Slingshot Network. It's now one of the products of HPE, Hewlett Packard Enterprise, that acquired Cray while we were working on this project back in 2019 or 2020. We are supporting on this infrastructure the number of compute nodes. As of today, we have AMD Rome that since 2020 multi-core nodes. We have NVIDIA A100 since 21, MI250X. This is the same compute node as you have on Cetonix in Perth at Porcy. And then we are we have installed this year the GH200. This is Grace Hopper, the latest development of NVIDIA. and you probably heard a lot about this in the news. We are the launch customer for this product. And we've been working on this since 2 years. And we are also deploying a sizable amount of MI300A, which is the successor to MI250X from AMD. And I will now, to help you imagine, I'll just take the GH200 and explain the way the infrastructure is built. So this is the super chip consisting of the Grace, an ARM multi-core processor, and the H100 GPU. And it's okay. So Grace 72-core CPU, ARM-based, and Hopper, the H100 GPU. From a memory point of view, the GPU has 96 gigabytes of high bandwidth memory, so 4 terabytes per second memory bandwidth. And it has on the CPU side these total of 128 gigabytes of low power LPDDR memory that's soldered in. So no longer DIMMs that you can arrange yourself. And the result of this is an extremely powerful also memory architecture on the CPU side. And then the two are connected by this NVLink at about 0.5 terabyte per second. And then these superchips are organized on a blade in 2 nodes. So this shows 2 nodes with the whole cooling infrastructure on top of it. They are liquid cooled. Each one of these is of the order of 700 watts. And the whole thing is probably running at 8 kilowatts. You know, when we were starting with this project back in 2015, the thinking of all this, there were people who are convinced that we will, the future are machines with 10 kilowatts at most per rack. Now we have 8 kilowatts in the blade, and we are going to surpass 10 kilowatts. So it's basically, the limit is how well can you cool. Okay, the density, the compute density is really taking a direction that's kind of worrisome, particularly if you then, you know, you scale this to thousands of these and you imagine how much power you need, and somebody has to pay for that. Okay, so then imagine one of these nodes, so 4 Grace hoppers, these chips I just showed, they are interconnected with this NVLink in a direct, so tetrahedron topology. So no switches, just direct links between the 4 devices. And then they are, each one of these devices is connected to the network with a 25 gigabytes per second link to the network, NIC. And Cetonix with MI250X, or El Capitan with the MI300 or the MI300 that we have in Alps, they all look pretty much the same. So now you have the next step. Well, the numbers of one of these in terms of memory is quite impressive, and this is very important because you can imagine we will have a lot of machine learning that will work on this infrastructure. And there, if you go to large models, you need this type of memory and strong network interconnect between those different nodes. But now imagine we have many network endpoints, so literally 10,000 of network endpoints. We have a number of different compute nodes. I already told you, multi-core, MI300, GH200. And we have different types of storage, network-attached storage infrastructure. And now imagine you can group, logically group these different endpoints with whatever they have attached in a certain way. You can partition the network and then create these groups, endow them with the appropriate software, and then you can create something that we call versatile software-defined cluster. When we put Bitstein onto this infrastructure, which will happen probably next month or the month after next, we will have a V cluster called Stein on Alps. Okay. Or when we talk about the cluster for MWA, and this is in fact operational now, we have one, I don't know the name, Victor, you know the MWA clusters, but they are, so we have V clusters that are currently operational and running the numerical weather forecasting, and we have also a cluster for example, HPC cluster for the Paul Scherrer Institute. Okay. Now, the advantage of taking this approach at the software level is actually that we can separate the concerns. And there are a number of reasons to do this. So one is we can now adapt the user environment to these different software-defined clusters. We can adapt the service management to these different communities behind the clusters, and we can adapt the infrastructure provisioning. User environment is tailored, can be tailored now, so it's no longer one size fits all for all communities or all applications, but it can be tailored to the communities. It's programmable resource access and scientific build service. The engineers that maintain one of these platforms, okay, I need to be strong, they are typically familiar with the domain. Then we have the service management, we have platform tenant administrator there, who is typically a system administrator, but can have, usually comes from a domain science, and it's then the people who are provisioning the infrastructure that are usually hard to come by, but you only need fewer of these than if you had, you know, many different clusters. And so, you know, another way to view this is you have this standard gray gray EX architecture that HP is selling today. There will be evolutions of this in the future. Endowed with some of the technologies, this V cluster technology, you need a Firecrest is a web accessible interface, and then a container deployment system, and that is high performance. And then on top of that, you can support these platforms. And now this is real, so it's not just a schema. We have, like I said, MWA that is since June operational on this infrastructure. We have this HPC cluster for the Paul Scherrer Institute, which is dealing with simulations and data analysis. And then we have already operational the LHC WLCG compliant cluster. And we are building these clusters for SKA and the Cherenkov telescope array. And like I said, these clusters that will replace Bitstein, operational within about a month. And we do have also a dedicated cluster on this infrastructure for this Swiss AI initiative that is building foundation models. And so this is a big initiative that is ramping up between EPFL here and ETH Zurich, and supporting a number of verticals. You can see the climate and sustainability vertical, clinical, public health, etc. So the same players, you know, that we have on the meteorology and climate side, they are also involved in this. And here you also see the kind of the revolution that's happening in science, that machine learning and AI is now getting into computational science in many places. Now, how does this scale? So we have this infrastructure in Lugano that can support about up to 20 megawatts. We have the Swiss network I was talking about, and we can tunnel through these networks to local infrastructure, for example, one here in Lausanne. And in fact, the Meteo Swiss service is running both here in Lausanne and in Lugano. And we've actually had already 2 experiences where it was essential to have them in 2 locations. The service would just continue to run, but we had serious infrastructure problem on one and the other place already. So we have, it does work, the concept. And it works even at European scale. So we are not there yet, but the vision is that 20 megawatts in Switzerland is not going to suffice for the scaling aspects that we need in science. And so we have this collaboration with this LUMI consortium. We are part of the LUMI consortium. And there the machine, you might have heard about it, is in, I'm wrapping up, is in Kayani, a site that can support around 200-300 megawatts of power. And so we can scale from the 20 megawatts in Switzerland to multiple 100 megawatt site in Europe. The 2 have the same architecture, as in principle we have the same architectures on Sectonics, and this is now the last slide. Given this, the possibility that we have with digital infrastructure for science, I think there are some thoughts that I want to suggest here for MWA and potentially SKA in the future. Namely, we heard from Stephen before that we're talking of 50 and maybe many times 50 petabytes, that you're not moving. It is not trivial to move and will not be trivial even in 10 or 20 years to move that scale of data around the globe. So I would suggest you think about moving the compute to the data or closer to the data. That means implement large infrastructures, which is already happening in both Perth or Western Australia and in South Africa. And so that's already happening. You do need to develop these continuous integration and development pipelines. And these are things you can do on infrastructure such as ALPS that exist today and already have these software practices and support. We can scale out in Europe to infrastructures like LUMI. The caveat there is usually the owner of the infrastructure, whether they let you do things or not. Technically, an amazing amount of things are possible. And then deploy production in form of these V clusters on infrastructure in Western Australia or South Africa. That's what I would do if I were, to make a suggestion on how to answer your question and work with MWA. And this is what I propose also, why the Swiss should join the MWA to really work to get, like we say in America, get it done. Okay, and then see where we take it from there. Okay, yeah. And the final point I'm making is the WLCG model, which we can support and we have experience with, is a completely different problem than what you're facing in radio astronomy. And so you should not copy that model. You should come up with your own. Okay, thank you. Thanks.
Any questions? Yes.
You talked about these type of chips that are well tuned for things like machine learning, where you have both large core and large RAM requirements. One of the things we run into often in radio requirements is we have a high RAM. So where exactly does radio astronomy then fit well into these more standardized approaches? That's very few people have that requirement.
Okay. So this we can also visit along with answer. when you look at one of these superchips, you can ask the question, where is the biggest cost? And I don't think the cost driver are the focus. The cost driver is the memory, particularly on the high memory. Because one is you need this high memory core, but you also need data from the memory. And so the cost in these things is the memory and the way you manage that is what it. So I have no problem if not the entire GPU or CPU is used. Now that said, I think one should still try to distance the memory over as many nodes as you can. And this is typically a mathematical exercise. I know there are many discussions about that, but that's where actually the need comes, but it's the question of how you define what you're trying to do and how you solve it.
Yes. Thanks for your talk. It's very interesting. I was just wondering, with a lot of radio astronomy workflows, some of the biggest challenges are in I/O. So a lot of our tasks are I/O bound rather than compute bound. Where do you see the I/O bottlenecks being relieved as time goes on? Are there any plans in the future?
Okay, so the key, I think, to this infrastructure is that the I/O system, so the disk system, whether it's disks or solid state disks, SSDs, is integrated into the network, the high performance network, and while the I/O is limping behind, even on our infrastructure, but mostly because of lack of clear strategies on how to develop software for that support I/O, but purely from a hardware point of view. And we need to invest in the software, these network attached memory models, whether it's NVMe over Fabric or so, is the way to go, and is giving you the best I/O performance. And when you look at the needs of the machine learning AI community, this is the beauty that we have today. There is a huge commercial requirement to improve the network at low cost and improve the injection and improve the storage system. So I'm completely confident that things are going in the right direction on ALPS, and they will accelerate in the right direction in the next 5 or 10 years. And available to anybody. The only problem we have is the price is going up, because there is a commercial demand, and that's a struggle. But that's going to be whatever solution you choose.
What level of data transfer are you willing to tolerate?
Between what?
Where do you draw the line?
Between data transfer, between, it's always a question, on the system we support.
Yeah, so for example, MWA data, so transfer from Pawsey in Perth to a computing centre, for example, in Switzerland.
Yeah.
So when you say petabytes are not feasible.
Yeah, you're asking me, what can you tolerate? I would say, what can you physically do without actually putting tapes in a plane and flying planes around, and then doing with all the logistics. In reality, Switzerland has one of the most advanced academic networks. Thanks to the railroad system, there's a lot of fiber that we can use, and we operate today at 400 gigabits per second. If we go to connect to Lumi, we can connect probably at 100, 200 gigabits. We're establishing a link to Bologna, and that's a dedicated link, currently 100 gigabits per second. If we go somewhere in Germany, we dive down to 20, 10. So I have my doubts that you can just using commercial networks move anywhere faster than 10 gigabits per second. And I guess to move a petabyte per hour, you need a terabit per second sustained, if I remember right. So don't ask me what I'm willing to tolerate, to ask what is economically feasible to move data at that rate around the globe.
Yeah, so I
From
think
places that are not so well connected.
one dimension that can be relaxed is the timescale. So we don't need a petabyte per hour to be transferred. Not even a petabyte per day or a petabyte per week, maybe.
Well, but you're producing, and the numbers I hear from SKA, astronomical amounts of data per time. And if you now want to have that data available, hundreds of petabytes per year, then you come to petabytes per day.
For the
And you
SKA,
don't sustain that with 10 gigabits per second.
for the SKA, yes.
Yeah.
But for the MWA, that's not the case.
Okay.
So I think there's a sweet spot
Yeah.
where we probably should be both bringing the compute to the data
Yeah.
and the data to the compute. So I think that those conditions will probably
Have to
prevail
be experienced, yeah, in reality.
for the next 5 to 10 years. I think
Yeah.
that's
Yeah.
a good
What
sweet
is
spot for the
practically
MWA.
possible? I think that's really the question.
Yeah.
What is practically economically possible? To find out.
Yeah.
But for example, just to give you one of the models we are pursuing with ECMWS, they produce half a petabyte per day today. They have an archive of 600-700 petabytes. Currently, I think this was 1 or 2 years ago, it's growing at probably 100-150 petabytes per year. And the solution we have is we have a data cube installed at Bologna with this dedicated link, and we move data inside the high performance network of ECMWF into that data cube, extract data, prepare it for machine learning, and then move it to us. So reduce it and move, reduce data. That's maybe a model one could explore. There are many things one could explore.
Cool.
Okay, good, thank you.
So I guess, yes, thank you, sir. There is a So thank you. So let me introduce Dr. Jade to take over for the presentation with RFI mitigation in MWA data.
Bonjour à tous. Hi, everyone. My name is Jade. I'm a PhD student at Brown University, and my talk today is titled US-based research on mitigating radio frequency interference for MWA data. And I'll be speaking on behalf of the US MWA SWIFT team. So before I get started, who is the US MWA SWIFT team? Well, SWIFT stands for Spectrum and Wireless Innovation Enabled by Future Technologies. It's an RFI-focused research group funded by the National Science Foundation. It brings together physicists from Brown University and the University of Washington. And our scientific focus is the epoch of reionization, something about here. So we are interested in 21 centimeter cosmology. And of course, since I'm here today, the instrument we use is the MWA. Here's a quick little overview of what I'll be talking about. I'll be starting with a brief introduction of what RFI is, how it shows up in our data, and why we really want to get rid of it, before moving on to the first half of my talk on RFI detection/flagging algorithms. So I'll go over a chi-squared-based algorithm that's been developed at Brown University, an algorithm based on the Hera watershed algorithm, a third one with a tentative name acronym EVILS, and the last one is a unit, so a machine-based learning algorithm. And then I'll move on to the second half of my talk on near-field interferometry. So I'll start with what are near-field corrections, and I'll explain how by combining these with a concept called beamforming, we can estimate the altitude of an RFI emitting source in our data. And I'll conclude with future directions for this research. All right, so getting started, radio frequency interference is a big problem for us. It contaminates MWA data and it obscures the 21 centimeter signal that we're interested in. And it's very difficult to predict and avoid because it comes from so many possible different sources, so airplanes, satellites, radio towers, and so on. It shows up in our data in so-called waterfall plots. So these are plots of the interferometric visibilities at each time and frequency in an observation. And they show up as bright streaks or rectangles in our data. And we already have several flagging algorithms that act on waterfall plots that have already been developed and are already in use with the MWA, such as AO Flagger and SINS. And so flagging simply consists in producing a Boolean array to mask the contaminated regions of data so that we can remove the affected data from the rest of our analysis. And the problem is that in some cases, this is a really difficult task. So how bright should a pixel be to count as RFI? What about its neighbors, and how do you fill in those gaps? Our current flagging algorithms tend to struggle with these questions, and that leads us to often unreliable flags. And additionally, there are some other complications. For example, within the same observations, some baselines will see RFI, such as the one on the left, it's very obvious, and some others will completely miss it. And that leads to the need to flag data on the so-called observation polarization level as opposed to the waterfall level. So for one observation, you'd want effectively to produce 4 flag arrays for the 4 polarizations, north, north, east, east, the 2 cross poles, instead of producing 8,000 or however many waterfalls baselines in your observation. And another complication here, I'll insist on the word seemingly. There's a recent paper, Walensky 2023, shows that ultra-faint RFI that is very difficult to detect still contaminates the power spectrum within the error window, and that deteriorates constraints on the 21 centimeter signal. And this really highlights the need for improved RFI mitigation strategies, which is what we've been working on. So in order to obtain more reliable flags, we are continuing to develop more and more sophisticated algorithms, and these are the ones I'll be talking about today. The X-Square from redundant calibration, Hero watershed algorithm adapted for the MWA evils, and the unit-based machine learning algorithm. And additionally, during the second half of the talk, I'll talk about how some near-field interferometry techniques can also help localizing RFI, with the ultimate goal being subtracting or excising it from the data completely. All right, the first detection algorithm I'll talk about is called the chi-squared RFI detection algorithm. It's based on the chi-squared metric from redundant calibration, and as the name suggests, it involves selecting down to only the redundant portion of the array, so selecting down only to the 2 hexagons, which we can do using PyUV data. And additionally, for this to work, we also have to average the time resolution to 18 seconds from the initial 2 seconds. So the 2 seconds with which this algorithm has been tested on. The data was with 2 seconds, we average it to 18 seconds to reduce the noise. And it involves running the redundant calibration using HeraCal. And this algorithm's goal is to solve for the complex gains by minimizing the chi-square. And if you had a perfectly redundant, successfully calibrated array, you expect the chi-square to be very similar at each time and frequency. But RFI biases this chi-square metric, which we can use to our advantage to help identify it. And the important note I included here is that while the RFI detection algorithm runs HeraCal, it only does so to get the chi-square. We don't actually use or look at the calibration solutions themselves. And on the next slide, we have some results from this. So the chi-squared metric I show on the top row in the x-axis and y-y polarizations, we see that it picks up some signal. The middle row is the same observation seen using SINS, and the bottom row is the same observation with AO Flagger. So we see that in this case, all 3 flagging algorithms pick up on some RFI signal in the same region. But what we found is that chi-squared can also identify RFI that is missed by the other 2. So here we have an RFI event that lasts throughout the entire observation. This is completely missed by SINS and not really picked up on by AO Flagger. This is a success of chi-squared. And on the next slide, I have the comparison view between chi-squared, SINS, and AO Flagger. And this pie chart, the percentages here add up to 100, and that doesn't mean that 100% of the observations were flags. This is of the observations that were found to contain RFI, this is the breakdown. And we see that 37% of them were only flagged by chi-squared. So it does provide a lot of complementary information. So these percentages were run on the whole MWA fall 2016 season data. On the next slide, this one will be a little harder to see, but this is the whole fall 2016 season. Every dot here corresponds to an observation. If the dot is full, it means that one of the flagging algorithms found RFI, and when the dot is empty, it didn't find anything. And here, I'll just zoom in to make one section a little bigger. We see that chi-squared is especially good at finding RFI that lasts throughout multiple observations, which are missed by the other two. So while the chi-squared metric is clearly able to identify RFI, work is still needed in order to turn it into a functioning flagger. So on the bottom here, we show just the result of a simple iterative flagging process. It doesn't flag the whole band. What we would want is to flag the whole Australian DTD channel 7 band, because we know this is a known RFI band. We know that the whole thing should be flagged. And it's not doing this at the moment. So a little bit more work is needed to turn it into a flagger, but it's definitely showing some very promising results. Our next flagging algorithm is based on the Hera watershed algorithm, which is the flagging algorithm currently used in the Hera analysis pipeline. And this algorithm runs via the XRFI module in Hera QM. And the approach involves treating the waterfall plots like topographical maps and flagging or flooding the neighborhood of a bright pixel that signals RFI up to a user-defined threshold, so watershed line. And the problem we had with adapting this to the MWA is that the coarse band lines confuse the algorithm. The coarse band lines to this algorithm, they look like RFI, but you don't actually want them to be flagged. They're not RFI. The solution we found was just simply remove them, flatten the data, run XRFI to detect the RFI, and then stitch the data back together. And once we got that working, we were able to produce a plot that's very similar to the one I just showed, except now we're including the new XRFI adapted for MWA. And although it's very hard to see, we noticed that it's performing comparably to our other flagging algorithms. So it's also providing some complementary information, and it seems to be doing a good enough job. All right, our third one has a tentative name, EVILS, for expected absolute visibility incoherent resolved spectra. And it works very similar to SINS, but skips the subtraction step. So for a given frequency channel and polarization, you take the average of the magnitudes of visibilities across all baselines, subtract the average of that in time, and finally compute a z-score with this equation. Now on the next slides, I have some results. On the top row here, so the columns here are just all the different polarizations, x, x, y, y, and the cross poles. On the top row, we have just the EVILS statistic itself. On the middle row, we have the EVILS z-score, and on the bottom row, for comparison, we included SINS. And if we start with the bottom row, we see that SINS shows some kind of signal on the bottom left plot, but it's really not obvious, while in the middle row, the EVILS statistics really picks up on it and would flag this as RFI. So this is still very much a work in progress, but as we can see, it is once again providing complementary information, and we're continuing to work on developing this. And the final flagging algorithm I'll talk about is a UNet, which is a machine learning-based approach. And the goal of this one is to feed in several waterfall plots from the same observation and obtain the corresponding flag array. Now, previous work on UNets has shown that UNets can successfully produce flags from one single waterfall plot. So the example I'm showing here is from the Kerrigan 2019 paper, where they're using one waterfall plot from Hera, passing it through the Kerrigan 2019 UNet, and obtaining a set of flags where orange here shows the true positive, so they're good flags. And we see that it's working pretty well, but no previous research on UNets with MWA data has been published, and this is what we've been working on. To show just a simplified diagram of the UNet, the idea is to feed in, like I said on the top left, all our waterfall plots, and have them go through a series of downsampling convolutions, reaching the latent space, and then upsampling it back up to the desired output shape. And that's why I call it a UNet. It kind of takes a U shape in this diagram. It effectively treats waterfall plots like images and applies a two-dimensional convolutional neural network at each layer. And the greatest challenge for this project has been the need for reliable ground truth flags, which are necessary to accurately train the model. As we've seen, all the traditional flagging approaches have their pros and cons, and we can't use any single one of them as the ground truth. And addressing this challenge requires the need for hand-labeled data, which is very labor-intensive. But further on in the presentation near the conclusion, I'll talk about what we are considering to, another method we'll consider to address this challenge. So that concludes the first half of my talk on flagging methods. And now I'll move on to the second half and talk about near-field interferometry. Okay, so to do a brief recap of near-field interferometry, standard interferometry assumes that the light sources are located in the far field. And under this assumption, light hits the antennas as plane waves. And since our astronomical sources are very far away, this is usually good enough for us. But sources of RFI are usually much closer in the so-called near field, and they emit curved wavefronts, and this curvature induces an additional phase difference between your baselines. And these additional differences can be corrected for. I'll show a diagram here for near-field corrections. Here we have a simple setup, one baseline consisting of antenna 1 and antenna 2, and they are looking at emission from an airplane that's at the phase center. And if that airplane were in the far field, then we would measure a W far field that's related to the far field planar wavefront. But because the airplane is so much closer, the way the light it emits is curved, and what we actually measure is W near field. We can calculate this W near field just using the geometry of the problem and obtain delta W. And this delta W depends on a lot of different parameters I'll talk about later, but maybe most obviously depends on the baseline itself, how far apart the antennas are. And the different near field delays experienced by different baselines leads them to placing the same object in different locations. So when you image this object, it looks blurry or a little out of focus. So here's an example. We're plotting just a single time step image in the narrow frequency range where the object was seen to emit RFI. We see that it's very blurry. But what we can do is apply the frequency, time, and baseline dependent delta W to each visibility, and that's going to allow us to bring the near field object into focus. And this was demonstrated recently in Bravo 2023, where the International Space Station was successfully resolved in an observation using these near field corrections. And if we take a look at what that looks like, when you apply the corrections, you see that the image immediately appears much sharper, and the airplane is brought into focus. But this delta W also depends on the distance to the source, which is not a priori known. So how do we get this? We will be using a technique called beamforming, which in this context refers to the process of averaging all visibilities together, which effectively concentrates the beam into one pixel at the phase center and returns the intensity of that pixel. So if you imagine your visibilities, they are complex values, they live in the IR plane. When you average them, what you're getting is the intensity of whatever you're phased to, whatever is at the phase center. And so the idea is to iterate through several values of the focal distance, because you don't know where the airplane is. So you need to iterate through several potential values of the focal distance, use beamforming at each iteration, and the maximum beamformed intensity should correspond to your optimal focal distance. It's an iterative process. But this assumes you already know the object's spatial coordinates, so right ascension declination, because without these, you also can't calculate delta W. If your object is bright enough, you can easily obtain this by making an image and then using WS-clean to find the centroids. Okay, and this movie shows the result of this technique. And before I hit play, I'll just quickly talk about what the 4 panels represent. So the top left panel is the iterative process I've just described. So we have on the x-axis the focal distance, on the y-axis the beam-formed intensity. And I wish I could move this thing. I'll just move it bottom here for now. Okay, there we go. Oh, that's better. Oh no, my movie. I wasn't ready. Okay, okay. Top right corner, this is just an image. So you're going to see the object as it's traveling through the observation. You're going to see it moving. Bottom left, this is the maximum value from the top left panel, converted to an altitude above sea level and plotted on the bottom left. And bottom right, this is just the angular displacement from the origin point of the airplane. So now I'll hit play. We'll just see how that works. So you should focus on the bottom left. So we see that at first it's a little shaky. It doesn't really know where the airplane is. But once the airplane gets really bright, we see that it really zeroes in around a certain altitude. The displacement is very stable as well. And we see on the top left that it's pretty, in most cases, the maximum beamformed intensity is really brighter than the rest, in most cases. So this seems to be working pretty well. And in fact, we can condense this movie into one single summary plot that looks a little like this. So on the x-axis, we have all the focal distance values that we tried, and on the y-axis, all the different time steps that we applied this to. And we see that it shows some high confidence in the focal distance predicted using beamforming. It's pretty narrow streak here. And if we convert this focal distance to an altitude above sea level, we can compare this with different potential sources of RFI, and here's what we obtained. We obtained that the altitude consistently hovers about 11.5 kilometers. So that basically has to be an airplane. If you combine the altitude with the radial displacement, you get a speed of about 790 kilometers per hour, which is also consistent with an airplane's cruising speed. So this result is the first conclusive airplane detection in MWA data. However, it's not a perfect technique. And once we tried this with other presumably airplane-containing observations, here's what we get. We see that from left to right, it gets progressively less and less confident. So on the left, this is the one I've been showing. This is a phase 1, 0.5 second resolution observation. In the middle, phase 1, 2 second resolution. And on the right, phase 2 compact, 2 second resolution. And the reasons why it's getting worse and worse, higher time resolution leads to less confident result because the airplane moves a lot in 2 seconds. So you can't approximate its spatial coordinates using one single pair of Arabic coordinates. It moves too much. And the reason the phase 2 compact data leads to less confident result is that this configuration features much shorter baselines, and shorter baselines see the near field closer because your baselines are closer together, so they're much less sensitive to whatever curvature from the object you're looking at. So in this case, the airplane is already in the far field, and if you apply near field corrections, it doesn't really do anything. And the last limitation is that the object needs to be bright enough to image so that you can obtain the spatial coordinates. So if your RFI is faint, then the image wouldn't be very good, and this technique would be harder to apply. And future directions for this include trying to subtract or excise the airplane from the data, which would allow us to retain a higher fraction of usable data. And another potential future direction would be that if we apply this technique to data containing RFI from a known origin, we can verify whether the object is also reflecting RFI in a different band. So here I've shown a photo from Dev where we see persistent narrowband emission from Starlink. It's very hard to see. It's inside this purple rectangle. We see very persistent emission from Starlink. So we know that Starlink is there, but we can't see whether or not it's also reflecting RFI in the other bands, because in that case, it would be too faint. But if we can apply the near field corrections, that could help bring the reflected RFI into focus, and we can figure out whether or not we're in trouble. All right, so I'm nearing the end of my talk, and I'm reaching the conclusion section now. So some concluding remarks. We are particularly excited about the prospects for the unit, because the ultimate goal here would be to establish a weak supervision framework where the flags from all the traditional methods are intelligently combined, and use the combined flags to build a solid ground truth for training purposes. And my last concluding remark is that RFI mitigation has indeed been shown to improve the EOR power spectrum limits for the 21 centimeter signal. So here is a comparison between the Beardsley 2016 analysis in purple and the Berry 2019 analysis in green. So they're using the exact same data, but one of the main differences between their two analyses is that in the 2019 paper, SINS was used in addition to AO flagger for RFI flagging. And we see that indeed the limits have been decreased thanks to this analysis for the exact same data. So this is why we're continuing to work on RFI mitigation. It has a real impact on our science, and that's it.
Yes. I think in a plot we showed the comparison between AO flagger, SINS, and chi-squared a Venn diagram, I think it was.
Yeah, yeah, I'll go find it.
Showed
Yes,
techniques there.
yes.
It looks like AO flagger doesn't find anything unique. So
Yeah, that's what we found out. It doesn't really do anything. So if you have to choose one, you should use SINS. Yeah.
It's actually the flagger also. We want to use them with sequences. AO flagger actually makes it harder to because it spreads flags and takes them out. This is tricky. So once we got success by sorry, I should have let it.
So in the case of the airplanes, even though we may have some poor temporal resolution, presumably we can assume that they're moving on a linear track. Can we actually then maybe do some modeling where we'll actually be able to go even beyond the temporal resolution issues?
So I don't know what slide I'm looking for. So in the case of the 2-second resolution, because it's moving, you mean
So presumably one can model this as a
Right.
moving source.
yeah, because we saw in the movie it's very stable.
Right.
It moves. Yeah.
So
Yeah, I think that could be interesting. Yeah. Especially because WS Clean is really hard to use. And so if I can avoid using WS Clean, that would be very good. So yeah, this could be interesting, definitely.
Did you try and get the ADS-B data for the plane in order to establish
Yes.
a ground truth for the measurement?
So we paid for a subscription to FlightAware, the API. Didn't find anything. So the problem is the observation is from 2013 and it just doesn't extend that far. They don't keep historical data that far. Maybe there is an API that does, but we weren't able to find it
I
really.
think the obvious solution is that we get an ADS-B receiver at the MWA. Collect our
Track them, right?
We probably should do that.
Yeah, just out of curiosity, is the Starlink signal, is that intended?
That one was it. I think that one was unintentional, and I think they fixed it. Right, I saw a paper recently. I think they've been working on fixing it.
Yeah, I'm just forwarding a question from the chat here. So someone's wondering how computationally expensive it is to find and fit and subtract an airplane compared to, say, just running AO flagger.
So the most computationally intensive part is the imaging step with WS Clean to actually find the RA deck of the source. It's maybe 1 or 2 hours on the supercomputing cluster for the whole thing. For example, this observation on the left, I think maybe around 2 hours of the whole, everything. So imaging, finding the sources, and the iterative beamforming. So, and about the RAM, I think you need about as much RAM as the size of the observation, and plus a little more. So it's like 16 gigabytes. I always give it a little extra. Yeah, it's not that bad, but it's for a single observation. So if you have to do this multiple times, it can get pretty expensive.
Thank you. This is the final talk session. Took a break. Will give us the Canadian perspective.
Oh, we'll do that.
To share that.
PDF one's fine. It's fine.
Okay. Okay.
One fancy transition. Oh, well, I'm not getting the wonderful ability to get that out of the way, but we'll be fine on this. So first off, thank you very much for inviting me here. For those of you who don't know me, my name is Gregory Silverkopf. I'm a professor at the University of Alberta in Edmonton, Alberta in Canada. My main science interests are in transients, but I've also done a fair bit of stuff regarding some of the data challenges for radio astronomy, as well as some multi-messenger and multi-wavelength astronomy. I'm also the new board member for Canada and the new lead of the Canadian Consortium. I'll talk a little bit about some of the changes that are going on. And what I want to basically do is I wanted to sort of give you some introduction to what's going on in radio astronomy in Canada and how that relates to the MWA, some resources that we have that I think we all can potentially use, but mainly I really want to use this opportunity to set the foundation for even stronger collaboration between MWA and Canadian astronomers. I'd also like to say that normally I start most of my talks with a land acknowledgement. It's very hard to do a land acknowledgement when you are trying to basically represent an entire country as large as Canada. So realistically, Canada's had a very difficult history, I would say, in terms of how we have interacted with Indigenous cultures. We are improving in that process, but it is an ongoing thing. Most of our land is, of course, Indigenous land. It's similar to the Australian condition, where we are, for the most part, coming from outside of the historical land use. So it's very much with this that I think countries like Canada, countries like Australia, maybe taking the lead in talking about different ways in which we interact with the Indigenous cultures, because we really need to be doing that, because we are definitely the ones that have most advantage from having done all the unfortunate interactions we've had with Indigenous cultures in the past. So I'm hopeful that astronomy can continue to improve that, and I'm very hopeful that actually instruments like the MWA can lead the way there and are leading the way there. I also apologize. I like talks with lots of pretty pictures. Talking about this type of stuff doesn't lead to many pretty pictures. I'll get rid of them mostly. There will be an animation, or was an animation here. I tried to take a 20,000 foot perspective on what's going on. And for most countries, you go through some type of decadal planning process. So in Canada, we call it the long range plan. We do it every decade, normally a year off of when the Americans do theirs, although we managed to get ours out before the Americans this time, which has advantages and disadvantages. And so I was very interested, even as someone in Canada, I was very interested to go and figure out what were the radio astronomy observatories that Canada listed as being things that we had going into the 2020s. Access to through international agreements, what we're already talking about here. And I broke things off only considering anything below 50 gigahertz. There's only 4. It shocks me because we're actually involved in many more, but for the most part, we haven't done as many formal agreements. That's starting to change. So ALMA, TRIME, which I will be showing you a picture of this. The MWA is one of them. And then we had 2 telescopes that are actually on the Dominion Radio Astronomy Observatory where time is also held. So these are our two international facilities, which is shocking to me. And these are this is our national facility, the Dominion Radio Astronomy Observatory, DRAO, NRC Hertzberg. Once upon a time, its name, or I think we can still call it NRC Hertzberg. The government makes us change names every 4 years, it seems. Largely, we have a 26-meter antenna and the east-west set of 9 7-meter antennas. Some science is getting done for these, but for the most part, I would say that these help us develop things, less get science. A lot of science work has gotten done with the Canadian Hydrogen Intensity mapping experiment, or CHIME. CHIME started very much focused on EOR type of science, and very rapidly we realized, oh, wait a minute, we can do FRBs with this. And that's basically what the vast majority of CHIME results have been on, are those fast radio bursts. The H1 people, they've got a long job. The ER people know this. Us transient people, we get all the fast science. You know, you guys have to do all the hard work. So this is our picture of what we had going in, and then we asked, so what are going to be our priorities for 2020? And you can sort of replace those 4 sets of instruments with another set of 4 instruments. ALMA continues to be a priority, and it barely squeaks in at under 50 gigahertz. CHIME, we're looking to build on CHIME with a slightly different approach. Now, instead of having these monolithic ski ramps or skateboard ramps, we have basically a small antenna that are going to be largely fixed position antenna. So they will be able to change their elevation, but we'll be doing that probably in cycles. So you'll have one elevation here for several months and then another elevation here for several months. The other aspect of CORD as well is that we're building outriggers to the CHIME telescope, so some of the CHIME array half pipes and other places, which is already getting some incredible science. We also have a lot of interest in NGVLA. Whether or not that occurs in this 2020, 2030 decade, I think that was very ambitious. And of course, the square kilometer array. And realistically, most of what we've been focusing on in Canada, especially from my perspective, has been the square kilometer array. It's our highest, it's the highest priority among the new priorities. We also have a large interest in the 30 million telescope or some other very large optical telescope, but that's ongoing issues. This was going to be what we were concentrating on, and we had no idea what level we were going to be able to participate in the SKA. So we took a shotgun approach where we tried to work on all different types of levels to actually prepare for the SKA. How many of you guys have ever used data from the CADC? Okay, only a small number of people raising their hands. The CADC is the Canadian Astronomy Data Center. It is, I may sound biased, but I'm not from Canada. I think it's one of the leading virtual observatory type of centers in the world. CADC and CDS to me are the 2 leads. No disrespect to anyone else. In terms of, they have a huge number of breadth and types of instruments that they actually work with. We also have something in Canada where we have national allocations of compute time. We work together, we got together, we created the Canadian Advanced Network for Astronomy Research. Really, all this is us putting in some big asks from our national allocations. And this was going to be our lowest effort, not low, but lowest effort with the lowest risk of failure. And normally you say low reward, but I would argue that we actually are getting moderate reward out of this. So we're building heavily on the CDC expertise. And a big thing as well, I'll say, is, which is great, I think most of radio astronomy is doing this, is we make the results open source. And I'll talk about why you might actually care about these things. And open source is almost always the answer why you care. I want to talk a little bit about CANFAR very quickly, because in thinking about SKA regional centers, you're going to have some kind of data science approach. And we've developed one in Canada that I'm very happy with, that's actually working really well. And it's not just Canadians using it, there's multiple groups involved with this. Normally a Canadian has to be leading it, but that's another issue. In particular, we switched from largely an OpenStack cloud way of doing our research to a browser-accessible container-based approach with the CANFAR Science Portal. Nowadays, I don't even think of buying computing anymore. I'm going to work on this. I'm going to work on some type of system similar on my university level. We've got a lot of stuff with storage management that can work over the web with command lines and with Python interface data. We call it VO space. There's a nice Python library. It has its ups, has its downs, but it's available there. Great group management software that interacts with all these other aspects. So you can manage your entire group, and even something thinking a little bit more ahead. This hasn't gotten as much traction yet with CANFAR, but we have a service where basically we link the data, store the data long-term for papers. This is with DOIs. And so more and more people are starting to do this. We have that service set up. And a lot of these you guys can get access to probably with a Canadian leading it. And so why do I think you might care about this low effort approach? I think this is going to be basically the blueprint for how SRCs are going to work. I think you're going to want to get in on the ground floor of working with these because there's going to be pros and cons as we go to this very much bring the compute to the data, bring the compute to the data model. Of course, the great news is you don't have to, buy the whole program. You can just use the bits and pieces. And this is expandable in the sense of as we increase Canadian allocation, we are increasing the amount of work that we can do. We will get to the point where I think we can't do all the research we want to do with the science platform due to computing limitation, but we're going to get around that, I think, with one of the later approaches. The real strength, I think, of Canadian radio astronomy lately has been this other program called the Canada Fund for Innovation. This is how we first built CHIME. This is a national competition every 2 to 3 years that allows for sort of $1 million scale projects. I say moderate effort. It was a crap ton of effort, but it's only a moderate effort compared to what a high level of effort is, which I'll talk about later. It has a moderate risk of failure. Normally 1 out of every 3 proposals that actually make it to going in are approved, and there's a very high competitive portions to even be allowed to submit from your university. We've had major collaborators from universities I won't necessarily mention, but whose names you would recognize, where they, part of a collaborative approach across Canada, their institution decided that they weren't going to get their part of the pie, and we had to redo our entire applications around them not being involved in it. So moderate risk of failure, and we do get moderate rewards. CHIME's only moderate on the scale of things. But in addition to CHIME, what I want to talk to you about is some of the more data science focused projects, namely these 2 things called Serata and CandyApp. A while ago, I realized that databases were something the CFI could fund. And then we were able to start selling radio astronomy data access as a database and convince them to actually fund us. So what does this mean? Well, we started with a sort of a pilot program to start getting tuned up for the radio astronomy data deluge. And the basic idea was to generate science-ready data products from a couple of different sources. So we worked with actually a range of SKA pathfinders, and the video, and sometimes somehow it's called SKA Pathfinder too. I'm a little confused about that, but so a big part of this and where I got involved was the Very Large Array Sky Survey. But we also had people working on ASCAP Wallaby, and we added 2 or 3 more modes of how CHIME could work. I'm not going to tell everything that Serata did. There's a website. You can go look at it if you want. But I'll give you an idea of something useful that we've done. Namely, we've got a nice little cutout server working now where you can get a fair bit of radio astronomy data all at the same time. for those of you who can't read that because it got blurred, Gleam is one of the things that we actually are serving, and I'm working with Natasha and trying to see basically if we can support a lot of the Gleam X serving of data. Many people make cutout services normally for your particular instrument. We're starting to get more and more where we're starting to build these cutout services for multiple instruments all at once. This is not the best answer out there. This is just one of many answers. But this is the type of thing that we're starting to build in terms of services. And I think this is probably if you ever wanted to see any VLAS data, any of the radio astronomy data, putting the time in to learn this, which is about 15 seconds, is well worth it. Now, if you want to do bulk batching, it's a little bit harder. So we did Sarada. We learned stuff, but of course the rule is these things have a finite timeline. So we had to put in a new proposal. At the same time, we knew that we were going to have to think a little bit bigger. One of the other major projects that got mentioned in our long-range plan, but which didn't have a clear funding step forward, was access to Rubin Observatory data. And especially if you're a transient scientist, boy, would you like to combine radio astronomy and optical astronomy transients. We also want to combine some multi-messenger facilities, which we can do. So we basically built our program around some of the same approaches we did with Sarada, but applying it now for multi-messenger approaches. I'll talk very quickly about the different parts of Candy Apple and then get to the why should you care, because really I hate doing the advertising on all of what we're doing. I care more much about why you care. So first off, we have some on-site hardware. The on-site hardware, we have about $500 million Canadian set aside to bring compute to the data in the form of putting a compute cluster that sits at IDEA in South Africa. So this would basically be the equivalent of saying we want to put a compute server down in the MWA, if we had thought of doing that. And this is not a small little computer, it's not a large computer, but it's nothing to sneeze at. And the idea here is to basically do the entire commensal science you can do with Meerkat, reduce the data as much as possible so that you can then ship only a fraction of that data back to Canada where we'll do the science with it. And in particular, we'll want to combine this with other telescopes and do a similar approach for something like the MWA. We got $500,000 towards the receiver upgrade. I'm sure that's the big reason why you should all care about Candy Apple from the short-term perspective. And we put a lot of money into compute hardware within Canada. I won't get into the politics of this. We don't actually have any control of where this goes, almost at this point. We put it in one particular center, but that was because that was the center we had the politics to do, not where we would actually like to put the data. So unfortunately, the bring the data to the science doesn't always work because there are politics always. But I think what's more important is it also has a lot of our funding for software development and software operations. So when we're doing things like building a community alert broker, for those of you who don't work in the transient world, it used to be that every now and then you get an email that something exciting is going off. With something like the Zwicky Transient Factory, you could potentially get 10,000 of those emails a day. It's going to go up with Rubin and the LSST surveys. So nowadays, you really need some type of way of dealing with all these alerts. And our idea here is nothing special in terms of we're not going to actually try to redo what Rubin is doing. We're going to just take what Rubin is doing, work with them, but start to integrate some of the SKA Pathfinder data. So this is where I'd like to be working closely with Gemma and the transient team to see what we can do in terms of alerts from MWA. But also, of course, with the Meerkat commensal data, et cetera. And any multi-messenger facilities where we have our hands into. In the transient world, we also then often need to take these alerts, combine them and go, is this something I want to spend time doing science with? And that's where a transient marshal comes in. You can imagine that this is sort of automated. Everyone's saying, ooh, I think I found something. Ooh, I think I found something. This is putting together and going, all right, do I care because two things found it, or there's a galaxy nearby and I care about galaxies, or whatever your definition of caring is. This is also, unfortunately, where you have to get rid of all the fun little artifacts. Transient marshals these days are still mainly human. They are becoming machines more and more. So the transient marshal is both the software and the person or the computer doing it. I don't need to tell you guys about automated pipeline processing. You guys do an awful lot of automated pipeline processing with MWA, even if you're doing it just for your own group. The size of your data, the fact that you need to often do multiple different experiments means you have to pipeline it. The interesting thing I think that we're taking, that I think will be something, if you're interested in data science, you want to think about, is how do you best work with all these changing data sets, even if the data itself is static. So I'm not even worried about the transient nature of this, but just the very much your data itself is what's transient. You know, you go through and all of a sudden, guy comes out with DR4. So now you have to rerun all your queries, etc. Well, what happened is instead of that, you had services that actually would notify you when your preconditions were met. All of a sudden, there are now 1,000 objects that are at a redshift between 2 and 3 and next to blue galaxies. I'm picking something randomly. The point is that you decide what the criteria are and that it tells you the data are available. Also, it means that you can go back and you have some way of dealing with the transient nature of your data in the sense of you'll know sort of which version of which different data sets you all have to deal with. And of course, you need something to put together. Portals are all the rage today. Multi-messengers is all the rage, so we just call it a multi-messenger portal. Realistically, multi-messenger is something we're keenly focused in, but also you got to remember we're competing with everyone else that's not a scientist even with this CFI proposals. From a science perspective, what we talked about for the MWA fits largely into basically transient stuff. But there are other things like magnetism of the universe, crystalline structure, star formation in galaxies, and weak lensing and dark matter, where there was some interest for broader things. That's not to say that MWA science doesn't fit in any of these, just we didn't highlight it in the limited space we have. Clearly, my interest is with transients, but I'm going to be working to get more and more Canadians involved, so it's not just a few of us involved. So why should you actually care? Well, yeah, we make science-free data products. Open source code, both Serata and Candy Apple will or are producing open source code. So you see something you like, go and grab it, change it, make it better. But of course, funding the MWA, helping fund the MWA research upgrade is probably the biggest reason this group does. We're looking right now to maximize what we can do collaboratively. Yes, there's what we put in the proposal. Yes, there's what we think we're going to do. But I can tell you that the cutout server for Serata wasn't in our proposal. It's the most used thing from our work, and we never thought we had to do it. We just realized we had to do it between proposal time and doing time. We had one more approach in Canada. This was going to be the highest amount of effort, the highest risk of failure, but the highest reward, joining SKO. And somehow we succeeded. I say somehow just because it was long viewed as an uphill battle, not just because of the money, but because to that point, Canada had never signed a treaty about science. We weren't worried about the money, we were worried about the politics. Why should you care? Part of this, we thought ahead and we put in a much more broad program for funding that included a fellowship program. We should be releasing details of this in the next month. You youngins out there, or sorry, early career researchers, please apply. We'd love to have you. But most importantly, we fully asked for our regional center as part of our ask. So like Australia, I think we've got to basically say we know we have our data center funding in hand, and now we've got to build it. More job openings. Also, a significant amount of computer and storage resources that I hope we can use collaboratively, like Stephen mentioned, like I mentioned earlier, and thinking about the models for all this. So, in conclusion, I know this has been a high-speed, low science type of talk, but I see that there's a lot of potential here. To answer your question, why am I here and Brian's not? Brian Gensler moved to the US. Or to leave a Canadian consortium when you're the dean of a US institution. So I'm taking over the leadership of the Canadian consortium after much discussion with the community. But I think that's also a good thing, not to say anything wrong with Brian, but it just means that whenever a new person comes in, they tend to try to reinvigorate stuff, and that's what I want to do. So I'm also keenly involved with SK in Canada. So building towards SK in Canada and building towards MWA in Canada are the same thing. So I'm going to be working to reinvigorate MWA interest in Canada. And what I really see, and Stephen didn't pay me to put this in, I won't name it. I see a lot of potential for us to work on some of these data center issues. Figure out how to do this the right way. How to maximize the times when you want to transfer data, when you don't want to transfer data. How to work on the user experience. Because for at least, the next 10, 15 years before AI replaces us too, we got that to think about. So thank you very much, and I'll be happy to answer any questions.
It's empty online too.
Okay then. Thank you so much.
I look forward to talking to you guys at lunch, or sorry, lunch. So, Stephen,
How many fellowships?
how many fellowships? On the order of 9 to 10 a year. Okay, so, sorry, on the order of 9 to 10.
Oh,
I say per year, in other words, that'll be the sort of the constant number. If they're going to be 3-year fellowships, then probably 3 or 4 a year, with standard turnover. So yeah, I think it's, yeah.
are you putting any thought into growing the ECR community locally? Because one of the things I've noticed as we all get our large amounts of money is that we're sort of cannibalizing each other's talent quite a lot. So are you putting any thought into not just making the pitch here to hire our people, which is cool, but growing up, growing the pool?
So
is there a program to support that?
So first off, one of the ideas of the program was to make it not be just the same old people getting the money. And so there's actually a support to within Canada to broaden the distribution of who's doing that research. There's actually, I didn't include any of this, but there was a huge amount of thought about development of human capital that went into the proposal. So we are very much keenly aware of that. However, the type of proposal that's in Candy Apple and the type of proposal that the SKA bid doesn't really allow us to actually put money into a earlier career pipeline. So we have to basically squeeze that in with our policies and less so with the money.
No question. Just a note from. Well, now's a question here.
Yeah.
Yeah. Okay. So I'm just reading aloud. Speaking from my experience as an MWA person who worked in Canada for a few years, I certainly agree that growing the local Canadian low-frequency radio astronomy cohort would be necessary. Okay, so it's not a question, just a statement. And then there's another note saying that she's very excited to see GleamX go up to Sereda.
That'll be Session.
Yeah.
Yeah.
That's great.
So this break for the fees, back, for this session 16.